So this is my synthesizer. I wanted to learn about modular synthesizers, so I built one. The colorful blinky light in the middle is a volunteer that got added to it today, but it's a great one. The oscilloscope down here at the bottom is for debugging, really doesn't have a whole lot to do with it. But the blinking lights and the chips up here and the rows of knobs, those are the important part.
That looks fantastic, I promise.
Hold it up again. Hold it up again.
You can come up later and, oh, Louie, would you please pass out the NDAs and get everyone to sign them? Okay. So, there's a ATtiny85 right there. I love those chips. They're like a little over $1. They're in a dip package, so they're easy to handle, easy to solder. They fit into a breadboard. And each unit on this modular synthesizer is one of these chips, a resistor on each of the two outputs. There's a digital output that goes to the LED. There's an analog output that goes through the resistor to that capacitor to smooth it out. There's two analog inputs here that are coming in on pins 2 and 3 from other chips. And there's a knob that comes in on pin number 7 here, which is the wire that you see on the other side of the LED is coming from the knob. So that's the basic structure. And I'm going to back up now and let's see, Control Shift plus. That's about right. So modular synthesizers were kind of invented, you know, in the, I don't know exactly when, but by the 60s, the Moog synthesizer was a thing, was being used by bands. I heard on the radio today someone was paying tribute to Tangerine Dream and to Jean-Michel Jarre for early synthesizer stuff, and they're still around and their stuff still rules. The idea of modular is that it's composed of lots of modules. Instead of being all wired together in one unit that just works, it's got all these holes and you have to put plugs inside the holes. And you get to choose which modules you put in it. And some of the real basic ones I've listed here. A voltage controlled oscillator is a unit that has a voltage going in and a sound comes out. And the higher the voltage, the higher the pitch of the sound. And it's usually logarithmic with a rule that there's 1 volt per octave. So if you're putting in 2 volts and you hear a certain pitch come out, if you raise it 1 volt to 3 volts, you know that the pitch is going to double and that it'll be 1 octave higher. Low frequency oscillator, as far as I know, is just like a VCO, but it puts out lower frequencies, or at least that's what my version of it does. Like I said, I'm new to all this, so anybody can correct me. I've got a sample and hold part that on some condition, it samples the input voltage and holds that voltage on the output line until it takes another sample. There's 2 of them on here. One is gated and one is periodic. The periodic automatically has a period, or you can turn the knob and change the period for how often it samples. The gated one takes basically a digital input. If it's above some threshold, then it's taking samples, and when it drops below that threshold again, it's holding. Voltage controlled filter. This is the hardest one on what I'm doing because you have to do a convolution, and that's a lot of mathematics to be run inside of a tight loop for a little processor that doesn't even have a multiply instruction. So that one's a little challenging, but I've got a version. Voltage controlled amplifier. I've been having problems with my implementation of that, and I'm trying to debug it right now. But how much it amplifies an input signal depends on another signal coming in. So on my board, the little CPUs here are digital chips are like normal microcontrollers. You program them, they're running machine code. But the inputs and the outputs that come through all the patch wires that are the ones sticking up, those are all analog signals. Just like on a real analog synthesizer, they would be analog signals. And what are those signals? I've listed a few types. One is just audio, where that's the kind that you run it into a speaker and you can hear it. There's frequency levels, which I mentioned before, the 1 volt per octave rule, and I observed that on mine. And then there's other levels, like how much to amplify or attenuate something in a voltage-controlled amplifier. Gates are what the synthesizer people call a signal which is used as a digital signal. It's considered to be either high or low, or sometimes it's a switch that's open or closed. And then there's this rule called patch anywhere. And this is part of where the fun comes in. You can connect anything to anything you want. And you end up, sometimes makes no noise at all. Sometimes it makes really interesting noises that no one's ever heard before, because you're being creative and you're doing new things. And on my design, as long as you're observing the things on the chips that are declared to be the inputs and the outputs, you can connect those any way you want to. There are other signals like ground and +5 that you don't want to connect to each other. So within reason, I observe the patch anywhere rule. And as I already told you, I love the ATtiny85s. They are not the latest thing. They're not the greatest thing, but they're a little over $1. They're in the 8-pin dip, really easy to use. They're robust. Earlier today, I had one plugged in backwards. It got a little hot, but still worked when I turned it around the correct way. You know, that's a great thing, that you don't have to. I don't ever worry also about, wrapping myself in aluminum foil and connecting myself to all the grounds around and stuff like that. I just pick them up and use them. They are the kid brother of the AT mega chips that are very popular because of Arduinos. The I/O functions are similar, usually subsets of Arduino, the same IDE and software. It ends up you're running G++, the GNU C++ compiler. So you've got a modern C++ that you can write in. The outputs can source or sink enough current to power an LED. And there's a neat little programmer, this red thing here, that plugs into the USB port of a Linux, a Mac, or a Windows in order to program. And you can see I've got a chip sitting in it. So the features of the ATtiny85 that I'm using a 16 megahertz internal clock. I'm using the analog to digital converter. There's 4 possible input pins. I'm using 3 of them. Taking just over 38,000 samples per second with 8-bit accuracy. If you went a little slower, you could get 10-bit accuracy, but my whole system's kind of 8-bit. I named 2 inputs, A and B, and then there's a knob, and I call that input K. And this is kind of important to understanding the constraints of what I've got. I sample A every other time. So the digital analog hardware is shared between these different inputs, and so I have to take turns. So I sample A every other time, so it's sampled a full 19,320 times per second with a Nyquist frequency around 9,600 hertz. So the highest frequencies I try to output are usually 8,000 hertz, 8,000 to 9,000. In the other time slot, I usually sample the B, but one time out of 256, I sample the knob K instead. That ends up sampling K 75 times a second, which is plenty for sampling a knob, and it only skips a beat every now and then on sampling the B input. Now for analog output, we have pulse width modulation instead of a real analog output. And there's possible to have 3 of them running at once. I only use one. It outputs short pulses at 250 kilohertz, and it varies the width or the duty cycle of those pulses so that either it's high most of the time or low most of the time or 50-50, and that simulates an analog output. I run it through a 200 ohm resistor, and then I have a 0.1 microfarad capacitor to the +5 power rail. If you multiply the 200 times 1 micro, you end up finding it's equivalent to about 50 kilohertz for the time constant, and that's logarithmically midway between the 250 kilohertz pulses that I want to get rid of and my Nyquist frequency around 10K that I want to keep. So it functions as a low-pass filter. Now, you don't really need to do that if you're running straight into headphones or a speaker, but if an analog output is being used as an analog input into another unit, you don't want it to see the pulses. You want it to see actual analog. So it's necessary to filter it. And any pin on the chip can be a digital input or output, and I put an LED for an output. And that LED, you can actually take it and use it as if it was an analog value as well, running it into something else. Now I've got a short interlude on debugging. When you're using these chips, you don't have a printf statement, you don't have a console. How do you know if the chip does nothing at all, which nothing it's doing? So I wrote 2 routines. The second one, fault, is the simplest. It stops all the interrupts and it produces a flashy LED doing a number of pulses that you can figure out, oh, this is fault 3, this is fault 5. Kind of like when your PC doesn't boot. You have to look at the flashing or the beeping to count. But the other one, I invented Moctal, which is like Morse plus octal. And I can output a byte with it, and I can output a byte while it's still running, while it's doing everything else, while the interrupts are flowing. So the example I give here is to output an octal 222, it does a long and a short pulse by flashing the LED. Dot it. So the short is the 0, the long is 1. And since it's a group of 2 and then 3 and then 3, when it repeats that, you know when you see the 2 that that's the beginning of it. And that was fun. And someone said, well, why don't you wire up an RS-232 output on one of the pins and run it off to a console? And my answer is I'm a ham, not a DCE or a DTE. I think a DCE. Data communications. What do they stand for?
Data carrier, data terminal.
Yeah, data terminal. Okay. So, part of my rules is that I have a standard module, and I had a picture of it here. Let's go minus a couple times. On my breadboard.
Triangle waves? Is that why that's TRI?
That TRI is a voltage-controlled oscillator to generate triangle waves. Yes. You know, I label them all with a 3 or 4 letter thing, because the only thing different in each cell is how I program the chip. Otherwise, every cell has got a resistor and an LED for the digital output, a resistor and a capacitor for the analog output, the knob coming in over here, and space for 2 signals to come in here. The unused pins, pin 1 is reset. It is possible to do stuff with it, but if you're not careful, you reset the chip. Pin 4 is for ground, and pin 8 is the +5 volts. And so this cell is repeated all the way down, and that's kind of a constraint that I live under. And you know, people say, well, why don't you do this and why don't you do that? And the answer is often, well, I kind of chose my constraints, and this is the way the game is played. So let's see, here I write that the chip has 5, that shouldn't have happened. There we go. Okay, has 5 useful I/O pins. So I have 3 inputs and 2 outputs, and you can see A and B coming in. the knob coming in off of the potentiometer. The outputs are named L and F, where L goes to the LED and F is my analog function output. And here I repeat those names. If there's an audio input, it comes in on A. If there's a control input, it comes in on B. And then there's some chips where you have to make up a different rule. K is for the knob, F is analog, L is digital. And the demo I was playing at the beginning looks something like this. I have 3 low-frequency oscillators, and they're in a ring. The output of this is the input to that, the output of that, and the input to this loops back around and goes back in. So that's a nonlinear function. Those are either sawtooth or triangle wave VCOs. And so it ends up making a kind of a chaotic loop. And so they kind of random what voltages are there at any time. And then the periodic hold picks a random sample out of there and holds it, puts it into the voltage-controlled oscillator, and then it finally goes into an echo chip. And that's what we were hearing before.
Can they do white noise? Do they like that white?
Yeah, I have a random number chip for white noise. It uses alleged RC4 crypto algorithm to.
Yeah, super high encryption. Right?
Yeah, I actually used the code straight out of the anonymous remailer when it was first released from the cypherpunk mailing list. And the comment there, the echo lets you hear the old tone for a while after the new tone comes in. And the hardest code has gone into my libraries. I called it Jerboa, which is like a jumping rat that thinks it's a kangaroo. In Jerboa.h, I've got all the classes, and so when you write your modules, all you need is the inputs and the ways of outputting things. And here is actual code for producing a Sawtooth Wave. There's a phase variable, which is 16 bits, and I sum the A input, the B input, and the knob to come up with a value which is somewhere from 0 to 3 times 256, because those are bytes. I look up in a table where I've pre-computed how much to increment the phase by, if that is the voltage coming in, and then I output the high byte of the phase as analog, and I output the high bit of the phase as the digital. And most of my modules are really just that short and that simple, and they kind of have to be because you can't do that much math inside the loop. Are you raising a hand?
So is what we're hearing right now, like, put in specifically, or is it all just completely random?
It's kind of random because it's those 3 low-frequency oscillators in a chaotic ring, and the periodic sample is picking whatever the voltage coming out of one of those is at the moment. And so that's the tone that you get, and then it picks another tone, and then another tone, and the echo kind of bleeds them together in time. So I think at this point, I'm going to stop the formal talk and say, come up here and look at it, and I'm going to pull all these wires out, and we'll start to build another patch a bit at a time if you want to hear what the modules sound like. Otherwise, you're dismissed. Or any other questions? All right. How you doing, Joe?
Sum all 3 inputs for a 0 to 15 volt input. Is that a 0 to 5 volt input?
No, I mean a virtual 15 volts. Each of these is like 0 to 5, 0 to 5, and 0 to 5.
I just learned something about coding. Thank you.
Yeah, that's right. And so if it's 1 volt per octave, this is capable of spanning 15 octaves. And you've never seen a keyboard with 15 octaves, but it runs from 8,000 hertz down to 0.1 hertz. And if I want high frequencies, say depending on this signal, I'll send both of these to +5 volts and we'll get high numbers. But if I want really, really low things, then I'll send these two to 0 and we'll vary that one and we'll get we'll have a super low frequency oscillator that way. That way I make one chip behave as a voltage controlled oscillator, as a low frequency oscillator, as a super low frequency oscillator. All right, you have learned something.
Every time I talk to you.
All right, anyway, come on up. I'm gonna pull all the patch cables out and I'm gonna make the individual pieces make noise if you wanna learn something about synthesizers.